Conservation of momentum. Suppose two objects, that is two balls A and B, of masses ma and mb are traveling in the same direction along a straight line at different velocities ua and ub respectively, and there are no other external unbalanced forces acting on them. Conservation means no change. Then the conservation of momentum means the momentum is does not changing, or the momentum remains constant over the time. Conservation of momentum is mostly used to describe the collision between the objects. The conservation of the momentum is only applicable to an isolated system of objects. Isolated system is a system that is not acted upon by an external force. That is, there are no other external unbalanced forces acting on them. In this theory, we are not going to consider any unbalanced forces. Suppose two objects of mass ma and mb are traveling in the same direction along a straight line at different velocities ua and ub respectively, and there are no other external unbalanced forces acting on them. Let ua is greater than ub and the two balls collide with each other as shown in figure. During collision, which lasts for a time t, the ball A exerts a force FAB on ball B and the ball B exerts a force FBA on ball A. Suppose VA and VB are the velocities of two balls A and B after the collision respectively. From equation momentum P equal to m into V, the momenta plural of momentum of ball A before and after the collision are MAUA and MAVA respectively. The rate of change of its momentum or FAB action force during the collision will be MA into VA minus UA by T. Similarly, the rate of change of momentum of ball B equal to FBA or reaction force during the collision will be MB into VB minus UB by T. According to the third law of motion, the force FAB exerted by ball A on ball B action force and the force FBA exerted by the ball B on ball A reaction force must be equal and opposite to each other. Therefore, FAB equal to negative FBA. The negative sign shows that force is equal and opposite each other, or MA into VA minus UA by T equal to minus MB into VB minus UB by T. By solving the equation, we get MAUA plus MBUB equal to MAVA plus MBVB. Since MAUA plus MBUB is the total momentum of the two balls A and B before the collision and MAVA plus MBVB is their total momentum after collision. From equation 9.7, we observe that the total momentum of the two balls remains unchanged or conserved, provided no other external force acts. As a result of this ideal collision experiment, we say that the sum of momenta of two objects before collision is equal to the sum of momenta after the collision, provided there is no external unbalanced force acting on them. This is known as the law of conservation of momentum. This statement can alternatively be given as the total momentum of the two objects is unchanged or conserved by the collision. Summary: conservation of momentum is used to describe collision between the objects. Total momentum of the system remains same, and this is called law of conservation of momentum. Activities and numerical application of conservation of momentum. Activity 9.5. Take a rubber balloon and inflate it fully. Tie its neck using a thread. Also using adhesive tape, fix a straw on the surface of this balloon. Pass a thread using this straw and hold one end of the thread in your hand or fix it on the wall. Ask your friend to hold the other end of the thread or fix it on a wall at some distance. This arrangement is shown in figure. Now remove the thread tied on the neck of the balloon. Let the air escape from the mouth of the balloon. Observe the direction in which the straw moves. The balloon moves in a direction opposite to that of air released from the balloon. When thread tied to its neck is removed, it is on account of the fact that escaping air carries a momentum towards one direction, and in turn an equal momentum is transferred to the balloon towards the other direction. From the activity, we conclude that in the absence of an external unbalanced force, the total momentum of a system remains conserved. Activity 9.6. Take a test tube of good quality glass material and put a small amount of water in it. Place a stop cork at the mouth of it. Now suspend the test tube horizontally by two strings or wires as shown in figure. Heat the test tube with a burner until water vaporizes and the cork blows out. Observe that the test tube recoils in the direction opposite to the direction of the cork. Initially, both the test tube and the cork are at rest. Their momentum is zero. As the cork blows out, it has a large forward momentum. To conserve momentum, the test tube receives an equal momentum in the backward direction and hence moves backward. Also, as the mass of the cork is smaller than that of the test tube, so it moves with larger velocity than the test tube. Thus, action and reaction are equal and opposite. Numerical problems. A bullet of mass 20 gram is horizontally fired with a velocity 150 meter per second from a pistol of mass 2 kg. What is the recoil velocity of the pistol? Solution. We have the mass of bullet m1 equal to 20 gram. We have to convert it into kilogram, then we will get 0.02 kg. And the mass of the pistol m2 equal to 2 kg. Initial velocities of the bullet u1 and the pistol u2 equal to 0 respectively. Before firing the bullet, the pistol and bullet are at rest. The final velocity of the bullet is equal to v1 equal to 150 meter per second. The direction of the bullet is taken from left to right. Let v be the recoil velocity of the bullet. Total momentum of the pistol and the bullet before the fire when the gun is at rest. According to the law of conservation of momentum, we have the equation m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. So, total momentum before firing is equal to m1 u1 plus m2 u2. We have to substitute the values of m1, m2 and u1 and u2. Here u1 and u2 is 0. So we get the answer 0 kg meter per second. Total momentum after the firing is equal to m1 v1 plus m2 v2. Here m1 is equal to 0.02 kg and v1 equal to 150 meter per second and m2 equal to 2 kg. V is the recoil velocity. By substituting the values in the equation, we get total momentum of the bullet and pistol after firing is equal to 3 plus 2v kg meter per second. According to the law of conservation of momentum, total momenta after the fire equal to total momenta before the fire. Then 3 plus 2 equal to 0. By solving the equation, we get the recoil velocity v equal to negative 1.5 meter per second. The negative sign indicates that the direction in which the pistol would recoil is opposite to that of bullet, that is right to left. A girl of mass 40 kg jumps with a horizontal velocity of 5 meter per second on a stationary cart with frictionless wheels. The mass of cart is 3 kg. What is her velocity as the cart starts moving? Assume that there is no external unbalanced force working in the horizontal direction. Solution. Let v be the velocity of the girl on the cart as the cart starts moving. The total momenta of the girl and the cart before the interaction is equal to m1 u1 plus m2 u2 is equal to 40 kg into 5 meter per second plus 3 kg into 0 meter per second equal to 200 kg meter per second. Total momenta after the interaction equal to m1 v1 plus m2 v2 equal to 40 plus 3 kg into v meter per second equal to 43 v kg meter per second. According to the law of conservation of momentum, the total momentum is conserved during the interaction. That is 43 v equal to 200. Therefore, v equal to 200 by 43 equal to 4.65 meter per second. The girl on the cart would move with a velocity of 4.65 meter per second in the direction in which the girl jumped. Next one, impulse. Impulse is defined as the product of force and time. Impulse is thus equal to change in momentum, that is force into time. According to second law of motion, force equal to rate of change of momentum, that is F equal to change of momentum by t. Therefore, change of momentum equal to F into t. Then impulse equal to change of momentum equal to F into t. That is all in this topic. Let us learn next chapter, gravitation, in our next topic. Thank you.